So we're gonna give you a warm welcome. We really appreciate you joining us tonight, and it's a late night, in a late time in the night in your local time zone, and we certainly appreciate it. I would actually pass on to Anurag Krishna on behalf of the in behalf of the president of the Student Engagement Committee of IC Impacts. He would be the person who will introduce officially our speaker tonight. Anurag, please.
Thank you so much, Salman. So first of all, warm welcome to Professor Moore. So the title of his talk today is Geomechanics of Trenchless Pipe Installation, Repair and Replacement. So here goes a bit of introduction about Dr. Ian Moore. So trained in Australia, Dr. Moore has been Canada Research Chair in Infrastructure Engineering at the Queen's University since 2001. He has more than 300 publications to his name, which examine conventional and trenchless construction of new and deteriorated water, sewer, and energy pipelines, and have underpinned dozens of contributions to North American and other international codes of buried pipe design practice. Research includes work clarifying the strength of new and deteriorated pipes, contributions to behavior of pipelines, pipes pulled into place using slip lining, pipe bursting and horizontal directional drilling, and studies of onshore and offshore oil and gas pipelines. Dr. Moore was the founding director of the Geoengineering Center at Queen's RMC and served in that role from 2002 to 2018, when he was appointed the head of Department of Civil Engineering at the Queen's University. Recognition for his work includes Best Paper Awards from the ASCE, CGS, CSCE, ICE, and NASTT, Research and Professional Service Medals from the Engineering Institute of Canada, the Engineering International Association of Computer Methods, and Advances in Geomechanics. Dr. Ian served as the editor of the Canadian Geotechnical Journal from 2007 to 2008 and is currently serving a 2-year term as the president of the Canadian Geotechnical Society. So once again, on behalf of the SIERA Group and the Student Engagement Committee of the IC Impacts, I wish to thank Professor Moore for accepting our invitation, and the floor is all yours.
Thank you so much. Well, it's a real honor for you to be interested in my work, and I'm really pleased that you reached out to me. And it's an opportunity for me to introduce you to, first of all, trenchless construction, which is a very valuable method of maintaining and enhancing our buried pipe infrastructure. And also to give you an introduction to the sort of research that I've been doing to advance our understanding of the mechanics of these types of systems. I don't know how many of you've actually ever visited Kingston, Ontario. It's a relatively small city. This is the downtown of Kingston during what we call the Big Dig. And normally we don't see the water supply pipes, the sewers, storm sewers, wastewater sewers, electricity, gas, steam, and telecommunications conduits. But when there's a big process like this of digging up the infrastructure and repairing it, or replacing it and then reburying it, we get to see the pipes. Now, most people think this is very disruptive and ugly and not very optimal. Of course, for a buried pipe researcher like me, of course, I love this type of project. But of course, if you owned a business on this street, you could be out of business in a month if your customers can't reach you. And a typical process like this takes many months to go right down the street. It's very costly, very disruptive. And so what I want to do is introduce you to a number of trenchless methods, or so-called no-dig technologies, developed to minimize how much we have to excavate to install pipes, to repair them and replace them. And here's some examples. On the left here, we have a directional drilling machine, and I'll talk a bit more about directional drilling in a few minutes. This is installing an oil pipeline under the North Saskatchewan River in Edmonton, Alberta, part of a project that one of my graduate students monitors. The middle upper photograph here is a part of a project of replacing a concrete sewer using static pipe bursting. And if I have the time, I will give you some illustration of that. Everything takes longer with Zoom. So depending on how the time goes, I may not get to that part of the presentation, but we'll see. On the right-hand side, we're seeing a new pipe being inserted into an old pipe. This is actually an old corrugated steel pipe that's been corroded. This is a process called slip lining. This project was in Northern Ontario, where you install a new pipe and then you grout the annulus or that zone between the outside of the new pipe and the inside of the old pipe. You grout it with concrete or a similar material. And then there's two other technologies there that I've also studied. What the middle photograph at the bottom is a spraying machine, a new technology developed in Colorado, which the 407 ETR, the big tollway that crosses from east to west across the Toronto area, they were interested in using this technology, so we were studying it at Queen's. And it involves spraying the inside of the test pipe with a grout. It's a little bit like shot creep of the sort that Dr. Nimi Banthia has been studying for many years. And then finally, the bottom right-hand corner shows a photograph of what's called a paved invert, where the corroded zone is covered with a layer of reinforced or unreinforced concrete. So we'll look at the geomechanics associated with these trenchless methods. I could also spend a presentation talking about the structural mechanics, but this particular presentation is primarily focused on the soil and rock mechanics, or the soil mechanics. I'll be illustrating the research as a combination of analytical work, computational work, and experimental work. And the goal is to develop design tools and guidance that consultants and contractors and others can use to ensure these projects go well. And I'll be summarising research progress we've made, and if I have time, I might say a few things about remaining research needs. And I'm going to focus on three technologies: directional drilling, and we'll look at research that I've done with a number of students to study the ability of the soil to contain the drilling mud without failure of the surrounding soil and loss of that drilling mud out into the environment. Second example I'm going to give you involves pipe repair, where instead of looking at the liner that's installed within the pipe, we're going to actually look at repairing the soil. And so we can get erosion voids forming due to water infiltration and erosion of the surrounding backfill. And we'll look at repair of that sort of defect using grouting. And then finally, if I have time, we'll look at pipe replacement using bursting, static pipe bursting, and specifically understand the disturbance that then results to the surrounding ground and the potential to break other utilities like water pipes, gas pipes, and so on as a result. So I've got some photographs here, or some images, some drawings, that illustrate the process of directional drilling. And you've probably seen this underway at various points around Vancouver or wherever you happen to be listening to this presentation. The idea is that the contractor has a special machine, a drilling rig, and that machine, first of all, angles down, and I'll show you a picture of another picture of a typical drilling machine in a moment, but it angles down from the surface, and the drill string, as they sort of add more and more of the drill rods, is then steered using a bit that can be steered so that it then goes horizontally under the obstruction. It could be a river, it could be a highway, a railway, maybe an environmentally sensitive area. So it goes under that obstruction, and then you direct it back up to the ground surface along that target profile. And then, using a bigger bit, you'll actually drill backwards, and perhaps backwards and forwards a number of times, to open that borehole up so that it's big enough to take a new pipe. And in that process, the borehole is stabilized using drilling mud. We'll talk a bit more about the mud in a moment. And then finally, after reaming, we direct the drilling string back to the exit pit, so the other side of the river. We attach the new pipe to the end of the drill string, and then we retract that drill string. We sort of recover it back to the left side of the picture, bit by bit, and as a result, pull the new pipe into place. So it's a way of drilling a hole for a new pipe and installing it into that new pipe. Now, one of the important geotechnical issues is the drilling mud. And the drilling mud is used to transport the cuttings. It's actually pumped into the borehole at the end of the drill string, at the cutting bit, that steerable bit, and then it's pumped back up to the ground surface, and it carries the cuttings, the soil particles that have been cut from the borehole back to the ground surface. It stabilizes the borehole so that it doesn't collapse, and it also acts to lubricate the pipe and cool the drill string as it's rotating and there's friction. But what can happen is if that mud is at excess pressure, it can cause what's politely called inadvertent returns. That's just a fancy way of saying that mud escapes from the borehole, travels through the soil up to the ground surface. And this photograph I've shown here is one I got off the internet, where it shows a drilling project out near somebody's home, where the mud has come up to the ground surface. You can see it bubbling up there and making a big mess. And there are jurisdictions in North America, such as California, where if that release of mud causes something like fish kill in a river, the contractor or the engineers responsible can end up in jail and certainly be sued. It also may cause surface uplift, so movement of the ground surface. I'm going to talk more about excess mud pressure and how we want to predict the limiting pressure that prevents mud from escaping from the borehole. Before I do that, I want to talk a little bit about what causes the mud pressure, what controls that mud pressure. First of all, we've got a column of fluid, that's the drilling mud, that's extending along that borehole up to the surface. So you can think of sort of a hydrostatic pressure, which is just the unit weight of that fluid, times the depth of that particular point, whatever point you're interested in, below the ground surface. So it's a height of column of mud reducing pressure. There's also viscosity, and particularly the cuttings, the soil cuttings in the mud, cause the mud to become more and more viscous as it gets dirtier and dirtier, as it gets more and more of those cuttings. And that viscosity means that then as you're pumping the mud back up to the surface through the borehole, you will get additional resistance to that and higher pressures. And so the contractor controls those pressures by controlling the quality of the drilling mud. He needs to keep cleaning the cuttings out of the mud, which is an expensive process. But the more he cleans, the less viscous it will be, the lower the density will be, and the lower the pressures. Now, I'm not going to say anything more about what causes that pressure, but just leave you with that comment that the contractor, an experienced contractor, understands that and will control the pressure. Now, I want to talk a little bit about the possible failure mechanisms, and this phenomenon is generally called what's called frac-out in the industry. But there are three potential mechanisms, two of which do not involve fracture of the surrounding soil. And the most important mechanism is resulting from shear failure of the surrounding soil, or what's also called blowout. And this is where that internal pressure within the borehole from the mud will cause the soil around the borehole to go into a state of shear failure, lose its ability to resist flow of that soil. And then if that zone of shear failure reaches the surface, we'll have mud flowing to the surface. We can also get tensile stresses, and the internal pressure within the borehole is stretching the outside circumference of that borehole and leading to incremental tension. And if that incremental tension exceeds the initial compression in the soil, we will get a zone of tension, and soil is very poor at supporting tension, and you'll get rapid propagation of a crack up to the ground surface. The third mechanism of mud flow to the surface is typically associated with heterogeneities in the soil. This might be a weak zone a weak layer of soil in the geological stratigraphy, or it could be an interface like the outside surface of an electricity or telegraph pole, where it's much easier for the soil to flow up that interface than it is to force its way through the soil. I'm not going to say anything more about those heterogeneities, but it's something that the contractor and the geotechnical engineer designing the project need to be very aware of. So the projects that I'm going to be describing to you in this presentation and this little section of the presentation on directional drilling relate to studying those mud loss mechanisms, developing finite element models that capture the mechanics, the undertaking of a parametric study using those finite element analyses, and then the development of simple design equations to estimate the pressure. And this is the work of 3 students, David Elwood, who's now a professor at University of Saskatchewan, Hongwei Jia, who worked in northern Alberta at Fort McMurray, and Haitao Lan, who is now a postdoc at Cambridge University. And I want to start by showing you a series of pictures illustrating the experiments, the beautiful experiments that Haitao Lan performed as part of his PhD. And this drawing on the left shows the vertical profile of the test pit. It's the smallest test pit we have at our geoengineering laboratory at Queen's. The pit is 2 meters wide and 2 meters deep, 4 meters long. We blocked off 2 meter length of that and filled it with sand. And then we opened a borehole of 38 millimeter diameter at various depths within that sand. And on the right-hand photograph, I'm showing one particular test. That dashed white rectangle is the surface, and below that location is the borehole at a certain depth. And those cubes that are on the surface are used to track the ground deformation using digital image correlation. So I have a colleague, Andy Take, who developed this technology when he was a student in the UK 20 years ago or something like that. And this is generally how we would map deformation patterns in a laboratory experiment of this kind. Now, I'm going to show you a number of photographs of the mud, the process of what that test looks like as the mud travels through the soil. And I'm going to relate it to this plot of mud pressure with time. So on the vertical axis, I've got mud pressure recorded in the borehole in kilopascals, and on the horizontal axis, we're showing the time of the test. And you can see that the mud pressure rises rapidly up to a peak, which in this test was 102 kilopascals, and then over a longer period of time, slowly declines to a value of 10.8 kilopascals. But let's look at what's actually happening in the soil during that process. So what Haitao did was a series of experiments where he stopped some of his experiments partway through this process. So he repeated this test condition a number of times. And by stopping the test partway through, he was able to then dig the sand out and see that part of the sand which had been saturated with the drilling mud. The drilling mud is a bentonite mixture. Bentonite is a clay that is very, that loves water. And we use it in things like diapers and in cat litter, amongst other things. So it's a very useful clay mineral, typically coming from Wyoming. And that mud will go out and travel through the soil, and by stopping the test at various points and then excavating, we can see where it's got to. And at this peak point, we do that excavation, we'll find that there's an annulus, which I've shown as a circle, but it's approximately circular, around the borehole where the mud's intruded and been forced into the sand. Now, a little bit later on, when we're now about halfway down that descending curve, we finally see something happening on the ground surface. And it's a little hard to see in that image, but what we're showing there is what Hightower is calling the primary crack. It sort of sits above the borehole and runs sort of parallel to the borehole axis. And that results because we're starting to get significant uplift of the surface, and that uplift is causing the top surface of the ground at that location to go into tension. But we don't see any mud. The mud is still confined within the soil. And then if you keep going and you exhume at this point 18.6 kilopascals, you'll see that the mud has partially traveled up to the ground surface. And it forms a series of what, not surprisingly, Hightower is calling secondary cracks. And then if you continue to allow that, to pump that mud into the borehole and the mud pressure drops, then finally you'll see the mud appearing at the ground surface over there at the side where I've got that orange rectangle. And so what's actually happened is that there are planes of shear that have developed up on either side of the borehole, along which that mud has flown. Now here's one of the exhumations that Hightower did, actually with another visiting student, and this shows those different components of the mud flow. It shows the approximate location of the borehole and that annulus of saturated sand where the mud has sort of gone out from the borehole and formed that annulus of mud. But then it shows a little, what Hightower's calling a flow tube, which is a sort of breakout point from that annulus of mud. And then one of those, there's a number of those protrusions try to develop, and then one of them goes up into a shear plane, and then we get a sort of plane of mud. And if you cut into that, it looks a bit like a jam sandwich or a peanut butter sandwich, where you've got a layer of pure bentonite mud, which looks like peanut butter, and beside that, of course, is the saturated sand, which looks a bit like the bread. So we've got a really clear idea of what the mechanism of flow is from the borehole up to the ground surface. Now, all of that experiment did was produce one measurement of peak pressure that the soil in that particular configuration can resist. So that is plotted here, that maximum pressure, that peak pressure we got to in that experiment, and it's plotted relative to the burial depth. Now, the burial depth is the distance h of the borehole from the soil, the ground surface, divided by the diameter of that borehole. So it's been normalized. And so this particular test was at about a depth of about 18 diameters. And then if you're willing to do many of these tests, of course, you can get a whole set of measurements and you can find out the relationship between maximum pressure, which is that pressure that the soil can resist before we have flow to the surface, versus burial depth. Now, I don't have time to go into the finite element analysis of this phenomenon, but Hightower, first of all, did three-dimensional finite element analysis of the experiment because the experiment was quite three-dimensional. Once he demonstrated that his three-dimensional finite element analysis was capable of giving us the correct behaviors, he then did a series of two-dimensional analyses, which is effectively what you have if you have a very long borehole rather than this short little experiment that we have in the laboratory. And then using those solutions from the finite element analysis, he was able to curve fit those parametric results and to find an equation, a simplified equation that could be used by a consultant or a contractor to predict the maximum pressure. And that maximum pressure is expressed as a ratio of that pressure to what's called the overburden stress. That's the weight of the overlying soil at that point in the ground divided by the water pressure in the soil. Subtract the water pressure in the soil, what's called the vertical effective stress. So that's on the left-hand side is this Tmax as a multiple of that effective overburden pressure. And on the right-hand side, we see the curve fit equation that Hightower developed, where he's giving the results as a function of burial depth or normalized burial depth. And then two soil parameters, the friction angle of the soil, phi, and the coefficient of lateral earth pressure, which is the ratio of the horizontal stresses in the ground to the vertical stresses. And this, I think you'd agree, is an equation that is easy to put into a spreadsheet and easy for a consultant or a contractor to use. Some conclusions. We have a parametric solution for mud pressure in sands, or the maximum mud pressure that can be used in sands. An expression that's dependent on these parameters that I just mentioned. Hightower also did experiments where he had loose material sitting over dense soil and dense soil sitting over loose soil, because of course soil stratigraphy is not always uniform. Often we have layered systems, and so we've developed recommendations on how to deal with stratified systems. We also measured surface uplift, or I didn't measure it, Hightower measured it, and so we have some guidance on how to estimate uplift of the surface, which we might need to know if we're trying to determine if this operation is going to damage other infrastructure. And we've got some guidance on not using some methods that have been reported in the literature, which we've proven are unsafe. I wanted to move on and talk a little bit about mud loss in clays, and understanding the mud loss mechanisms in those materials, and establish what controls them. And again, develop a parametric solution. And this is the work of Matt Kennedy, a different student who's now a consultant, senior consultant in Ottawa, Hongwei Shah and Haital Lam, who I mentioned before. Now, Hongwei was able to develop a closed form solution. That's an exact analytical solution for the case of blowout. This is this failure mechanism where we get unconfined plastic flow. Now, my purpose of this presentation is not to take you through this equation or explain how it was derived, but just simply to tell you that there is an equation that you can reference, or that can be referenced by consultants, that they will be able to predict maximum mud pressure based on these variables. SU is the strength of the clay soil that we're talking about here. Again, K0's that lateral earth pressure coefficient, in addition to G, the shear modulus of the soil. We also looked at the tensile fracture mechanism, where you get the incremental tension as the borehole expands, and you get that sort of circumferential tension, and what maximum pressure you can permit in order to resist that maximum pressure. And it's just, or resist that mud pressure. And it's just simply the mud pressure multiplied by 3 minus K0 if that earth pressure coefficient is less than 1, and P0 times 3K0 minus 1 if that earth pressure coefficient is greater than 1. And this plot shows on the vertical axis maximum mud pressures, which will cause failure and loss of drilling mud, versus this parameter that I've mentioned a couple of times, this coefficient of lateral earth pressure at rest. That's the ratio of the horizontal stresses in the ground to the vertical stresses. And what it shows is that there's sort of 3 zones that we need to think about. A zone on the left, that larger central zone, and a zone on the right. And I'll talk a little bit more about them. And this is a set of calculations for one particular set of geometry and mud and soil properties as shown on the right. In that central section, we're getting blowout. We're getting unconfined shear failure of the surrounding soil, and then flow of the mud up to the ground surface. And we can get either failure at the crown and flow from the crown, which is the top of the borehole, or we can get failure and flow of material from the spring line, that's the sides of the borehole. Now, this second zone, the one on the left and the one on the right, there are 2 zones where we can get tensile fracture, either at the spring line or at the crown, if we have coefficient of lateral earth pressure at rest, which is a long way from 1. And this last little comment I'm going to make is put this research that we've done in the context of current state-of-the-art analysis by consultants and current simplified contractor practice. And I want to start by talking a little bit about what contractors do. A rule of thumb that they often use is to say that they can use 1 psi of pressure, of mud pressure, for every foot of burial of that borehole from the ground surface. So it's a very simple equation or a simple relationship, but it's a relationship which ignores most of the controlling factors. The only thing it's really considering is the weight of the overlying soil. It's ignoring the strength of the soil, and more importantly, it's ignoring the ratio of the borehole diameter to the burial depth and the shear strength of the soil. And you can see that in some cases, it's a conservative estimate, but in other cases, it's unsafe. And then the red line, or the so-called Delft equation, is kind of the state of the art. And it's a blowout equation, which is based on an assumption that the horizontal stresses in the ground are equal to the vertical stresses. And we can see here that that matches Hongwei-Zha's closed form solution for the specific case, of course, of K equals 1. But at any other K-naught ratio, so if the horizontal stress is less than the vertical, or if the horizontal stresses are greater than the vertical, then the Delft solution, which is now commonly being used by consultants, or was being commonly used before this research, that Delft solution produces an unsafe estimate of maximum mud pressure. So again, the conclusion is that there are some equations that consultants and contractors can use. We can determine what is the critical failure mechanism and use those equations to calculate maximum mud pressure. And we've seen that both the contractor 1 psi per foot rule and the Delft equation are oversimplistic or unsafe. So that ends the first part of my presentation. In the second part of my presentation, I wanted to talk a little bit about deteriorated pipe repair. And in this slide, I'm showing a number of different ways of repairing a pipe, a deteriorated pipe. I already mentioned slip lining towards the beginning of the presentation, and the picture on the top left-hand corner shows a new polyethylene pipe being slipped into place within an old corroded corrugated steel structure, and then once it slipped in place, there'd be grouting, and the picture on the bottom left actually shows the grouting of that structure using a simple standpipe that's drilled, so they just drill from the surface through the top of the corrugated steel. They've installed a simple PVC, vertical PVC pipe, and they're applying that grout just through that standpipe. The two photographs in the center show a pipe repair process using what's called a cured in place polymer liner. And in this case, we take a tube or a sock, if you like, a fabric sock, very long sock, that's been impregnated with a thermosetting polymer like epoxy or polyester. It's pulled into place inside the old pipe. In this case, it's a cast iron water pipe. This project was a study that I did in the city of Hamilton, just west of Toronto. And then what happens is that hot water under pressure is pumped into that sock. That saturated or resin saturated sock is inflated and pushed against the inside surface of the old pipe, and then the hot water causes the thermosetting polymer to cure. Excuse me. Sometimes they will use steam. Sometimes they will, for larger structures like culverts, they'll use UV light, a little bit like dentists use when they're using polymer fillings for teeth. And then the technique on the right that I'm showing is that sprayed liner process that I mentioned earlier. And the picture on the bottom right is the result of spraying cementitious material on the inside of a deteriorated structure. Now, I've done a lot of work on the structural characteristics of that system, But as I mentioned earlier, this presentation this afternoon, or I should say, yeah, this afternoon for you, this evening for me, what I'm focusing on is deterioration of the soil. And what will happen is if once we have, say, perforation of a steel structure after corrosion, what we can then have is ingress or flow inwards of surrounding groundwater into that culvert. And as that water flows into the culvert, it will create an erosion void. And that middle photograph is one that I took just north of Kingston. I was able to get a decent photograph. It's hard to do in the field, but I was able to get a decent photograph of that void that was forming beside one particular pipe structure. And then if we don't control that erosion, the picture on the bottom right of this screen is what can result. And this was actually what happened when a corrugated steel culvert in Ottawa, Ontario, the erosion void became so large that it came up under the road over the top. And of course, you can sort of see the poor man that was driving this car ended up in this sinkhole. And it looks like a sinkhole, and it is a sinkhole formed by this erosion void. And the poor man, he had to climb out. The other motorist stopped and helped him out. And the newspaper headline read, "Sinkhole swallows car," and definitely not something that you want to happen to you. So this research involves trying to understand how that erosion void will affect the pipe that it's next to. And the work that I'm going to show you is aimed at understanding the impact of that sort of erosion void on either a rigid pipe on the left, so some computer analysis. That could be a vitrified clay sewer, or it could be a reinforced concrete sewer or culvert. Or on the right, there's a little model experiment at 1/4. Actually, that's a full-scale pipe that's sitting in this transparent box. And we're able to see the water flow and the development and the process of developing that erosion void. And I want to talk a little bit about the work of two of the students. So that's 3 students' work that's presented in these 3 photographs. And I want to present the work of Sean Tan, who's a mid-career engineer now with S&C Lavalin Nuclear Division. Jane Peter, who's an engineer in Toronto with Thurber these days, and Van Mai, who's working for a geotechnical consulting company in the Greater Toronto area. And so the first thing I did in studying this was about 14 years ago with Sean Tan. And what we did was we did some simple numerical, I'll call them numerical experiments, where we examined the impact of an erosion void developing beside a rigid pipe. And essentially what happens is, as that erosion void develops, the bending moments in that pipe increase. So the key design limit for a rigid pipe like a clay sewer or a reinforced concrete pipe is the bending moments that develop because the horizontal stresses in the ground are less than the vertical stresses. And that difference in stress leads to high bending moments at the crown, that's the top of the pipe, and the invert, that's the bottom of the pipe. And the impact of the erosion void is to reduce the horizontal stresses against the side of the pipe and lead to an increase in the difference between that vertical and horizontal stress. And the more that horizontal stress decreases, the more the bending moments increase. And this plot just simply presents a summary of the range of moment increases you would get considering various erosion voids of different widths and different sorts of soil. And the measure of the size of the erosion void we're using in this figure is what we call the void angle. That's the angle from the center axis of the pipe of that contact zone between the void and the outside geometry of the pipe. So that angle, it's like the angular contact between the erosion void and the pipe. And as it gets larger and more of the side of the pipe loses its soil support, the bending moments increase. I wanted to now show you some experiments in our test facility at Queen's, the larger test facility, where we've, or should say Jane, has instrumented a reinforced concrete pipe, and using optical fibers and particle image velocimetry, using conventional strain gauges, we've been able to monitor pipe deformations as well as strains. Here's a picture of Jane's test pipes in the pit, where we've dug a trench, put the pipes down, and just prior to backfilling. And she's got two pipe configurations there. One, where we've simulated an erosion void. This is not an erosion void actually caused by water flow. It's just caused, or it was generated using an air bladder attached to the side of the pipe, much as the location where you might see one in the field. So that's the concrete pipe there on the left with that black geosynthetic covering an air bladder. And on that pipe on the right is our control experiment, where we're going to be burying the pipe and it's going to have good soil as if it's a new pipe before erosion. There's a couple of other things I wanted to point out in this photograph, or these two photographs. You can see that there's a vertical pipe sticking out of that simulated erosion void, which is going to come up to the ground surface. Because these experiments are quite expensive, the scale of them is significant, and so we want to get as much information from one experiment as we possibly can. And so after testing the pipe and finding out how bending moments are affected by the void, we then explored what is the impact of filling that void, repairing that void with grout, and then retesting to see how bending moments develop with that sort of that cavity filled with grout. Now on the right-hand picture, I'm showing the way we simulate a pair of wheels at the end of a truck axle. And so what we can do is simulate truck loading or wheel loading from a truck, or a pair of wheels actually on the end of a truck axle. And above that steel column you're seeing there in the photograph is a 2000 kilonewton actuator. And so we can basically test it up to its strength limits. And that blue plate that you see in the image is the size of a standard Canadian highway design wheel pair. Now, I don't have a lot of time to show results, but I'm going to show one set of results where we've measured strain on the inside and the outside of surfaces of the concrete pipe, and then using the differences in strain, calculated the curvature, the distribution of curvature around the pipe resulting from that vehicle load, and then using the section properties and the modulus of the concrete, calculated the bending moment, the experimental bending moment that was developed in this test. And I'm showing two distributions, and this is a polar distribution, so it's sort of showing the pattern of moments right around the circumference. So the top of the pipe is at the top of the drawing, the bottom of the pipe, or the inverts, at the bottom of the pipe of the drawing, and of course the sides, or the spring lines of the pipe, are at the sides of the drawing. And the maximum moment we get when the soil is intact in this particular experiment was 1.9 kilonewton meters per meter. The maximum moment when we had a small void, as shown in that picture in the bottom left-hand corner, was 3.2 kilonewtons, sufficient to cause the pipe to reach its strength limit state. And if we compare that increase in moment that we saw because of the void to the calculations that I was reporting on earlier in this presentation, we can put that experimental data point that Jane generated within that XY plot, and it's that red triangle that you see, and there's her pipe specimen exhumed from the test pit. We did test that pipe after we filled the void, and you can see we can actually see the void there because it's on that lower left-hand side of the pipe with the grout that's shown. And so this gives us some confidence that the analysis in this particular instance is giving us something that's similar to what we're seeing in an experiment. Because of course we don't believe anything that comes from a computer until we've got physical evidence. So it's guilty until proven innocent if it comes from a computer or an analytical solution, because we don't know if the approximations we've made are really valid. And so, of course, the value of an experiment is we get to evaluate those approximations. So time's getting away, and I think I'll probably finish my presentation with this, this slide. So some conclusions from this study of erosion voids. The first thing I wanted to point out was that when we attempt to do an experiment with a larger void, that larger void actually collapsed under the simulated truck load before we got to the fully factored surface loads. In other words, before we got to the load that the Canadian Highway Bridge Design Code indicates the structure needs to be able to support. And so what we're seeing there is evidence of this type of, the way the void will compromise the safety of the road when a vehicle comes driving along it. We used grouting. We used air-entrained grouts, or a relatively low-density grout, and we found that it partially restored the soil support. So the large void moment was reduced to 1.3 times the intact soil case. And actually that's within the design limits of the Canadian Highway Bridge Design Code. So it brought it back into a safe zone. And then since doing this work, I've had another student, Tyler Monteith, who's actually done full-scale experiments of a leaking concrete pipe using our newest test facility, funded a few years ago by the Canada Foundation for Innovation, where we actually had leakage and we had erosion developing as a result of water flow. And we've seen similar increases in bending moment resulting from erosion. So I think I'm going to finish my presentation there. I don't have time to go through this final thing. I just wanted to acknowledge some of the my colleagues and international collaborators on this work, Drs. Brackman, Chapman, Holt, Skinner, and Take. The graduate students who've done these beautiful experiments, beautiful analyses, and I've mentioned them. I've tried to emphasize their role in the research. Graham Boyd, the technologist that helped me do these large-scale experiments, and my sponsors, Canada Foundation for Innovation, the Ontario Government, the Natural Sciences and Engineering Research Council, the Canada Research Chairs, because I have a Tier 1 Canada Research Chair, and then the companies that have provided the test pipes and so on through the Ontario Concrete Pipe Association, UCUB Canada, IPEX, and UPNOR Infrared Technology. So thank you very much for your attention, and I'd be very happy to take questions.